Great. Hello, everyone, and welcome to today's seminar in the Smart Safety Connection series. My name is Wesley Mon, and I'm the 2023 to 2024 Safety 21 Equity and Diversity in Transportation Fellow. This seminar series is sponsored by Safety 21 as an opportunity for faculty to showcase their current transportation projects and research. It's also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with research, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Excuse me. Please note this session is being recorded. If you're on Zoom, all participants' microphones are muted, and if you have a question on any time on Zoom, please feel free to send that in the chat box. Now I'd like to introduce today's speaker. Noosheen Nazari is an assistant professor of civil engineering at the University of Texas, Rio Grande Valley. She's a faculty affiliate of the NSF Crest Center for Multidisciplinary Research Excellence in Cyber-Physical Infrastructure Systems at UT and Safety 21. Her research interest is in human-centered smart transportation systems, crossing disciplines such as economics, psychology, computer science, and mathematics. Her research has appeared in premier transportation journals and major conferences, and she's actively served the professional community through journal editorial board membership and paper review, as well as technical committee membership. Now, please help me welcome Professor Nazari as she tells us about her project, the role of perceived safety concerns on public acceptance of behavior of autonomous vehicles. Thank you.
Hello, everyone. Can you hear me? I would appreciate if you could verify that you hear me. And also, I have started sharing my screen. Can you see my screen?
Yes, we can hear you. We can see the screen. Thank you.
Okay, thank you so much. Hello, everyone. My name is Noosheen. I'm very glad to be here to talk about the research I've done. The topic of my presentation today is on the role of safety concerns on adoption behavior of autonomous vehicles. Before starting the topic on adoption of autonomous vehicles, adoption behavior of autonomous vehicles, and safety concerns that people have about this technology, before that, let's see some numbers. Let's check the statistics and see how people think about safety of this technology. According to the AAA poll in 2023, 68% of Americans are afraid of autonomous vehicles or AVs. And this number has increased from 55% from the previous year. And it shows that it's not concern about safety as this technology was not only at the beginning of introduction of this technology, let's say like 2 decades ago. This trust has decreased over years. And one of these, for instance, one of the incidents that contribute to people's concern about safety is the practical test of these vehicles on the roadways. For instance, as you see in the picture on the left side, Waymo was involved in a crash in Arizona in 2018. Even though the AB was not didn't have the fault was not AB's, but still it had a negative effect on people's safety concern. Another statistics that we can talk about is from Statistica. As you see on the right graph, people are asked about safety, comparing safety of AV technology with typical vehicles, and most of people, as you see on the red bars and the gray bars, most of people think that this technology is less safe than typical vehicles. In addition to that, one of the main findings of our previous study was that people's acceptance behavior of AV is affected by the concern about different aspects of AV, and this is one of the most important factors. So considering all that, it's all of these motivated us to focus more on the safety aspect of AV and see how people actually perceive it and how their perception affects their opinion about AV. In addition to safety concern, let's see how people think about AV given their travel pattern. One of the benefits of AV that people in this area talk about is travel time saving of AV, is accessibility that AV gives us, giving a point-to-point access, door-to-door mobility, etc. And all this depends on how people's travel pattern is, meaning that people with different travel pattern, people with different travel behavior have different understanding of these benefits. And this travel pattern cannot be kind of summarized as only one number for the population we are investigating the problem. For instance, as you see in this map, travel pattern, let's say summarized by vehicles mile traveled, it has a distribution in the US states. And we cannot just take, for instance, an average value and put it in our model and simply saying that, okay, people's behavior can be represented by one number. If I want to say in a mathematical way, there is a heterogeneity of travel behavior of people, and this heterogeneity differently affects people's perception of AV and consequently their acceptance behavior. So all these motivated us to understand people's current travel behavior, see how their opinion about AV is affected by current travel behavior. In addition, their safety perception about safety concern about AV, and see how this concern affects their opinion about AV. But the challenge is considering all of them at the same time is methodologically challenging. Investigating adoption behavior of AVs, investigating perceived concern of AV and seeing the effect of this concern on AV adoption, modeling travel pattern, and at the same time seeing the effect of travel pattern on AV adoption, seeing them kind of estimating all of them together at the same time is challenging. But let's break it down into a simpler kind of mathematical format so we can deal with it. Based on the research question we have selected three kind of variables as the outcome variables of the model we are going to formulate. One variable shows people's acceptance of AV. Second variable shows how people perceive safety concern of AV. And the third variable shows people's travel pattern represented by the vehicle miles people travel annually. So we have summarized all these research questions as three outcome variables that we are going to model. So considering these three variables in your, considering all these three variables, let's see how we can mathematically formulate it. As I mentioned in my previous slide, we have intention to accept AV shown by the yellow box in the bottom of the page. We have concern about AV shown by the middle box, and also vehicle miles traveled or VMT in the top box. And we want to develop a model that at the same time can estimate all these three and see the effects of these variables on each other. To do so, we have adopted a recursive modeling approach, which is called recursive trivariate model. And depending on the type of variables we have selected the type of model we want. Two of the variables we have here, y2 and y3, have ordinal nature, and one of them has continuous nature. VMT is a continuous variable. So considering all these, we have come up with three equations representing the three outcome variables we want to model. About the rest of the variables in the equation, I'm going to talk about them in the next slide. First, let's come up with a way to estimate these outcome variables at the same time and see their effects on each other at the same time. The typical approach to do that is to eliminate the effects of the error terms of these equations have on each other. But what we have done in here is relaxing that assumption, meaning that the error term of VMT, safety concern, and AV acceptance are not assumed to be zero correlated. The correlation they have, the impacts they have on each other are taken into account in this method. How, as you see in the equation at the bottom of the page, epsilon 1, epsilon 3, and 2 and 3 are assumed to have normal distribution with zero mean and variance and covariance as shown in this matrix, which means that epsilon 1 and 2 are related by rho 1, 2, epsilon 1 and 3, the error terms of two equations are shown by rho 1, 3, and the last one by rho 2, 3. This is the first assumption that we have relaxed in this method. Other than that, as I said in my previous slides, we want to model people's concern about safety, but at the same time, we want to know how this perception affects their adoption behavior. We want to model people's travel pattern. At the same time, we want to know how this travel pattern affects their AV acceptance. To do that, we need to relax another assumption of typical models, and that assumption relates to endogeneity, meaning that, for instance, VMT is estimated and at the same time goes into the equation of safety concern and goes to the equation of AV acceptance, and safety concern goes to the equation of AV acceptance with related parameter. And this relaxes the assumption that expectation of the error components with these given variables, they are not considered to be zero anymore. Now we have three equations, y1, y2, y3, each representing one of the outcome variables I talked about. Now let's see how we can estimate this model, how we can implement it on a data set to get the results. To do so, we should first write down the probability equation for that. The probability equation, as you see in this equation, is the joint probability of y1, y2, and y3. And to calculate it, we broke it down into, using conditional probability, the basic rule, we broke it down into two components. The first component is the probability of y2 and y3 conditional on y1. And the second component is the probability of y1. And y1 shows VMT, y2 safety concern, and y3 AV acceptance. The second component is easier to calculate, given that VMT is estimated using a linear equation here, and we have a linear function. So the probability for that is written using the standard normal density function, given the exogenous variables that we have. But the first component is the challenging part here, which has a conditional probability. P y2, y3 conditional on y1. Let's first write down how the probability looks like. As you see in this equation, we try to expand the equation as you see here, but we have a conditional probability in the equation. As you see, we should get rid of that. We should convert it to another equation. So the probability can be estimable. To do that, let's start with the error components. The error components of y2 and y3 can be written conditional on error component of equation 1, as you see in this matrix. Now let's work on it to see how we can convert y2 and y3 to be conditional on y1. This is for y2, as you see in the equation. And this is for y3, as you see in this equation. And considering that, as you see, this on y3 conditional on y1, one of the components is the endogeneity of y2. So if we replace it with the former equation, we can come up with something like this. And the error component at the end can be replaced by something new. These new error components have standard normal distribution. So we have converted conditional probability to something that we can work with, something that we are familiar with. Standard normal, the error terms have become standard normal distribution. They are bivariate, so we can work with them. We have kind of got rid of the conditional probability. So the error components are written here, the distribution of them, and then it's passed to the probability equation that we had at first. We had the conditional probability. We could get rid of the conditional part. So we have something that we can easily estimate. All the parameters here are something that can be calculated by the distribution, the normal distribution of the error component, as you see here. So the probability function that had a conditional factor, we could get rid of that and come up with a straightforward one, as you see in this slide. Now let's replace everything that we have come up in the main probability equation. In two previous slides I showed you, we have the joint probability of y1, y2, and y3 because we are going to estimate it jointly, considering the endogeneity effect. The likelihood function, as you see, is written here, which is something calculable. It's estimated on the sample of individuals that I'm going to talk about in the next slides. So for each individual, it's written and then summed up over all individuals, and then we can easily estimate it. Why do we need it? Because we need to determine model parameters. By model parameters, I mean the parameters related to the assumptions I mentioned, in addition to the exogenous factors, the factors impacting safety concern, AV adoption, and VMT. But to add one point to our modeling framework, as I mentioned in the previous slides, we have 3 outcome variables: AV adoption, AV safety, and travel pattern. We want to model them simultaneously. Methodologically, we kind of dealt with the assumptions that we relaxed here. But there is another point about our model. The classical models that investigate humans' decision on every kind of choice, every kind of decision making, the typical models, the classical models, only look at the observed factors. For instance, if we use the classical models to see how people adopt AVs, the observed factors can be demographics. We see the impact of demographics on their AV adoption behavior and simply model it. But this black box of human decision is can be kind of more clear by looking at more factors other than what we can observe. For instance, if we want to model human decision as their adoption behavior, we can say that, okay, high income people, let's see the impact of income on their adoption behavior. But it's not enough because income doesn't completely represent how people think, how people the people's behavior cannot be captured only by income or other demographic factors. So we should take into account other factors that are called kind of unobserved or latent to the analyst. And these latent factors explain individuals' attitude or perception or preferences beyond the observed variables like demographics, built environment factors, and so on. So in addition to the joint estimation that we are going to do, we have also included the unobserved characteristics of individuals into our model. So if I want to summarize the whole modeling, the whole equations and modeling framework I talked about, we have 3 outcome variables, as you see in the yellow boxes, and we have 2 kind of exogenous variables. One is observed one, the other one is unobserved, but it's kind of related to the observed one. I will talk about them in the next slides. In the unobserved factors that I talked about, now let's mathematically formulate them first, and then we will move to the estimation process. These unobserved factors are called latent factors or latent constructs, and they kind of capture how people perceive different, for instance, features of a vehicle. This is what we have considered here. Perception of people about vehicle cost, not the actual cost of the AV, how in general people think about prefer vehicle cost. Second factor we considered is about vehicle reliability, how people perceive it. Next is vehicle performance, vehicle refueling, and shared mobility services. And as the name suggests, they are latent factors, meaning that they are kind of hidden for us. So we should find a way to capture them. How? For each factor, we define a number of indicators, and people's responses to these indicators can be related to these latent factors, and at the same time to the demographic factors. So we can mathematically capture them and be able to explain them. And the model for that is the model we have used for that is a structure equation model with latent variables. Now let's go to the estimation part of the problem. We have formulated the problem, the joint model with indigeneity and also latent factors in addition to observed factors. And we want to estimate the model on a sample data set. We have selected a sample from California, and the outcome variables, the 3 outcome variables are Two of them have ordinal nature and one of them has a continuous nature. The ordinal ones are AV acceptance and AV safety concern. As you see here in the coded sentences, how AV acceptance is explained to individuals are described here, and also there's the safety concern. And these ordinal outcomes range from 1 to 5, from strongly agree to strongly disagree, meaning that persons have responded to question on, for instance, AV acceptance from the range 1 to 5. Do you accept AV with this condition? Strongly disagree, neutral, agree, and strongly agree. The same thing for AV safety concern. Let's take a look at the distribution of the sample over these questions. As you see here, the top part shows AV safety concern, the bottom shows AV acceptance, each with 5 levels. Well, as expected, people are observed mostly to be concerned about the safety concern, and they disagree with the acceptance of AV, mostly disagree. The third outcome variable we considered is travel pattern represented by vehicle miles traveled, or VMT, and the distribution of VMT on the sample data set we have is shown in this graph. As you see, most of people have the annual VMT of less than around 10,000 miles per year, and you see the average and cumulative distribution. The other variables we have in the data sets are related to the exogenous variables I talked about, the demographic variables like gender, race, education, household structure, household income, and the residential factor. You see the distribution of these factors on the sample data set, the impacts that the results we got. I will talk about them in the next slides. Here is just the distribution of these factors on the sample. And also the latent constructs I talked about. We have a number of questions called indicators measuring those latent factors. You see the distribution of these indicators over the sample. For instance, on average, people are more concerned about the initial price of a vehicle and also the MPG of a vehicle. They are also concerned about reliability, which marks one of the top 3 reported factors. The last kind of indicators you see the distribution here relates to shared mobility services. People's preference for these services are captured using 3 types of indicators. One is the level of using car sharing services. By car sharing, I mean services like Car2Go, or like that you can rent a car for a limited number of hours. The second type of services are ride sharing, like Uber and Lyft, that we can hail for a short ride. And the third type of indicator is captures people's opinion about how these services affect your future vehicle decision. And as you see, people tend to disagree with this, but still there are, like, let's say 15% of them that completely agree that these ride-sharing services affect their future decision about vehicle. Now let's go to having these data sets prepared and ready, and our method formulated. Now let's estimate the model, see what we found. The first part of the estimation is on the structural equation with latent construct. To have some values on the latent construct so we can pass it to the joint model. First, let's evaluate the SEM model. As you see here, all the goodness of fit measures meet the related criteria. Now let's check the results. For the sake, I don't go through all of them for the sake of time, but if I want to mention important ones, all of them are found to be, all the values you see are found to be significant. For instance, individuals' opinion about vehicle cost is one of the factors, and vehicle initial price plays a more important role. Reliability is another factor capturing people's preference for vehicle reliability in general, not just about AV. Then we are going to pass it to the main model and see how this, for instance, the perception about reliability affects on their opinion about AVs. And for shared mobility, the indicators are found to be significant. The next part of the structural equation model is about exogenous factors. For instance, females are found to be more giving more attention to vehicle cost than like reliability, performance, and refueling performance. Or people that have more children in their household care about more about vehicle performance and shared mobility than vehicle reliability or cost. Now that we have estimated the latent construct using structural equation model, we have them ready to pass it to the main model. So let's go to the main model. We have other exogenous variables as well ready to test their effects on the main model. The main model is, as I explained in the methodology section, is a recursive trivariate model with 2 ordinal outcomes and 1 continuous one. Before going to the results and see what findings are, let's first check the assumptions we had in the methodology section on simultaneous estimation of the model and endogeneity, and see if we could statistically approve our the assumptions we did at first. So the first assumption is about the joint estimation of the model. We have compared the result, the three criteria of our recursive model with their univariate counterparts. So we have estimated a joint model and also a model which is not joined. The error components are not correlated. And in terms of AIC, BIC, and restricted rho squared, we see that the recursive model outperforms the univariate counterparts. So we cannot reject our first hypothesis on the joint estimation of the 3 outcomes. How about the second hypothesis we had? It's on the endogeneity impact, meaning that the safety concern is affected by some factors at the same time impacts AV acceptance. VMT is affected by some factors at the same time impacts safety concern and AV acceptance. This is labeled as endogeneity. Let's first statistically check if this hypothesis is working or not. As you see, we have done some comparisons here with some restricted models. One restricted model is a model with 0 correlation. Another one is with absent recursivity. And the model we estimated in comparison with both of them works better. And also the parameter of safety concern in AV acceptance, parameter of VMT in AV acceptance, and safety concern, they are all found to be statistically significant, meaning that our second hypothesis cannot be rejected. Hypothesis on endogeneity cannot be rejected as well. But let's see what they mean in terms of the value we found and also the sign of the parameter. Well, as expected, safety concern negatively affects AV acceptance, and VMT has a negative impact on AV acceptance. It means that people with who drive more likely are not that much interested in AV. How we can use it for policy implications and so on, I'm going to talk about it in the next slides in our conclusion section. How about AV safety concern? People who drive more are less concerned with AV safety aspects. Again, how we can take benefit of this finding to work on our policy suggestion, I'm going to talk about in the last slides. Now let's go to the latent construct that I talked about. Other than the exogenous factors we consider in this model, we had 5 different latent constructs that capture people's attitude and preferences other than their demographics, their residential factors, and so on. So it's kind of attitude-driven variables. Now let's see which one are found to be more significant and important on the outcome variables we had. People who care about vehicle costs are less interested in AV. Well, it makes sense. And people care about reliability, and they are less concerned about AV safety issues. And also people using shared mobility are less concerned about AV safety aspects. Again, how we can benefit from these findings for policy suggestion, I'm going to talk about in the next slides. The other factors we considered are demographic factors. You see the impact of the significant parameters we found in the model in this table. For the sake of time, I don't go through all of them, but for instance, females are more concerned about safety of AV. People with higher education, higher than postgraduate or above or beyond, are less concerned about safety of AV. Let's see how having kids in the household affects our perception about AV. People with more kids are found to be more interested in AV, especially if their children are teenagers. And obviously, the high-income people are more interested than low-income. How about residential factors? One interesting finding of our study is about parking costs. People who already have free parking are not that much interested in AV, even though they drive more. And also, daily parking cost in dollar per day has a negative effect on EVMT, as we could imagine. How about the vehicle decision, the type of involvement of household members in their vehicle decisions? If in a household, decisions on purchasing, adopting a vehicle is made jointly with all members, they are less interested in AV and they are less concerned about the safety factors. Using the estimation results, we calculated the marginal impacts of all the factors. I don't go into the details. I just quickly go to the policy discussion that we can conclude from the marginal impacts of the exogenous factors. One of them, the first finding that we had in this study was that preference for vehicle cost and perceived safety concern are 2 most important factors in AV acceptance behavior, meaning that policies designed for policies that want to encourage AV acceptance need to focus on these factors other than the other ones. For instance, policies on cost incentives can be designed by lowering interest financing for AVs, cash rebates, and so on. or trust building programs can be developed, like technology demonstration, public education campaigns, and so on. And they all positively impact people's opinion about AV. But this is something that the other studies have also verified. What distinguishes our study from the other ones is to suggesting a way to effectively design this policy. What does it mean? It means that the policies I talked about, who should we focus on? Who are the most important cohorts of individuals that we should focus to if we want to make AV popular? The results of our findings suggest that if we focus these policies about safety concern and vehicle cost, if we focus on shared mobility users, we can get better results because shared mobility use is found to have a significant impact on AV safety concern. How about other cohorts of people? Those that are that have vehicle reliability awareness in general, not just about AVs, they are the second cohorts of people that can be focused on to get more kind of return of investment that if we want to invest in any policy decisions. And about the demographic factors, one of the factors found to be the most influential ones is gender. So we should close this gender gap if we want to, again, make, as I said, make AVs popular, because females are compared to males are found to be cost conscious and safety concerned. The other findings of ours are this study relates to the impact of travel pattern. As I said in the first slides, we wanted to know how individuals' current travel pattern impacts their AV opinion about AV. This travel pattern is captured by VMT, annual VMT, and we found that this VMT has a negative impact in AV acceptance. What can we understand from this is that this finding challenges two potential AV benefits in vehicle travel time saving and the impact of AV on urban sprawl, because one of the benefits of AV is mentioned to be that people can enjoy from people can get rid of the driving task and get involved in other tasks, but we see that for those who drive more, this feature gets less attractive. And also one suggestion of about AV consequences that we may see some urban sprawl, but our finding shows that this may not happen because more AV leads to less interest in AV. And our last finding in this study is about the comparison of all these factors on people's different opinion about AV. What do I mean? I mean that all the policy decisions I talked about impact on those who have strong opinion about disagreement with AV, not those that are neutral or have moderate opinion about AV. And this is based on the sensitivity analysis we did on the model. Thank you for your attention. Please let me know if there is any question.
We have a question.
Sure.
Speak. Can you hear me?
Yeah.
Okay. So just the last bit of when you talk about the potential of the urban sprawl. So based on what I've seen in your model is that you use VMT and then find correlation of VMT to the acceptance of AV. But I think in the case of urban sprawl, it's more like that acceptance of AV is correlated to the VMT is going to happen because there's a potential that go further and live further away from city center. I think you speak a bit about that there is a paper that support or disagree with that. What's your opinion on that?
Thank you for your question. Let me. In our study, we investigated the impact of VMT on AV acceptance, and what we have concluded here is a kind of a policy implication, and this is just a suggestion because one of the benefits of not the consequences of the AV that people are talking about is that so people may tend to drive more, may change their house location, so they drive more and they live outside of the urban area. But our finding shows that people with larger VMT have less interest in AV. What we have concluded here is with caution, and we may say that we may not see urban sprawl in future because larger VMT people have less interest in AV. So if people change their house location, they may not be interested in AV. So we may rethink about what we told about urban sprawl at the beginning.
So I'm just trying to tie various parts of your presentation together. In the beginning, you mentioned that around 60 to 70% of people, I think it was like 67% of people had a negative view of AV. If I think of, I forget the name of the shape, it talks about the early majority being 34%, late majority being 34%, which is kind of like 68% of the population. I'm assuming that may be similar, but if I'm one of the innovators, early adopters, and I actually had a conversation where someone asked me, what are your thoughts on AV? And I thought, well, you have artificial intelligence that's driving AV, and artificial intelligence, just like in cybersecurity, has to be trained on models, has to be trained on data. And if you have very few accidents in the data, your model is not going to learn about the accidents. And then someone like me is gonna, I joined the crowd of saying, I don't have reliability, I don't believe AVs are reliable yet because the AI that's driving it is not trained yet on enough good data. Any thoughts on that?
Well, yes, I completely agree with you. That's why we see that companies, for instance, like Waymo, they do A/B testing in real world to probably to gather more data. So they train, they model, they make them better, of course. And the accidents happens are kind of since they are few data points on that, we may not be able to make a general conclusion. I agree with you, but the point we talked about here is that since the beginning introduction of AV, people there are a significant number of people concerned about this technology, and over time that companies, for instance, industrial people are working on improving the AV. Still, there are concerned about the safety aspect of AV, and it has not decreased; it has increased. So, when we are talking about acceptance behavior of people, we should give more. We should focus more on the safety concern of people rather than, for instance, the travel time saving or other features of AV. I wanted to kind of highlight the importance of safety aspect of AV when we are talking about acceptance behavior of people.
Anyone else?
Can I ask a question? You said that shared mobile services would lead to more acceptance of AVs. I would think a more direct comparison might be partial automation systems. They're becoming pretty widespread now, so more and more people have experience with partial automation of one kind or another.
Yes, I completely agree. What we investigated here was based on the data we had at hand. One of the factors related to kind of, let's say, technology, vehicle technology was using shared mobility. So because of the data set, we had a limitation of defining the variables, but I completely agree that these days people experience with partial automation with different companies, not just luxury vehicles, even with mediocre vehicles, people experience partial automation. So that factor comes into play more and more every day.
Thank you.
I have a question about kind of a personal anecdote, and then also curious about, you've looked into this, maybe next step. So I am an electric car owner myself, but we also have a gas-powered car that we've had for a long time, right? And did you look at or think about how many people who have a fully electric car do not have a secondary car? My concerns with it were range and things like that, right? But I live in the city. So I'm just curious if that's another step on like how many electric car owners also have a gas-powered car, right? Does that help with the issues of the urban sprawl you're talking about, or the VMT, the larger annual VMT?
Yes. Again, I agree with your comment. Thank you for raising that. Well, if we see electric cars as again kind of the available technology we have in the vehicle market, and also something that is restricting us in terms of VMT, seeing the impact of this factor in the model is kind of crucial, and it can be a suggestion for future research that see the impact of this VMT is not something like unbounded. It has some limitation, especially for people living in non-urban areas, have fully electric vehicle, for instance, and their VMT is limited. So how this the kind of availability to the mileage can affect their opinion about AV.
Yeah, thanks.
Could you quickly clarify, because I'm not quite sure what you mean by AV safety, because at the end there are two parties involved, in my opinion. It's the people in the car that make an active choice to maybe be subject to the additional risk or not. I don't know, it depends on what you think, right? And they're the people that are maybe just walking around in an autonomous vehicle, and they might also be subject to an increased or decreased risk. So maybe I missed it in the presentation, but yeah, go ahead, sorry.
Sure. As you see in this slide, the way AV safety concern is described to the respondents is that I'm concerned about the safety of self-driving cars. This is a quote I copied from the questionnaire, the survey that is conducted, and we kind of represented by the term AV safety concern or perceived safety concern.
Okay, so the second one is the exact question from the questionnaire that you asked them in order to assess their concern about being around an autonomous vehicle.
Yes.
Okay. Thank you.
Sure.
Any other questions? Well, thank you so much, Professor Nazari, for sharing your work, and thank you everyone for joining us today. A recording of this presentation will be up on the Safety 21 What's Happening page, and for the students in the room that are interested in Transportation Club potentially, definitely try to join that as soon as possible on Tartan Connect, because we're having our first general meeting of the semester on Wednesday in Hamburg Hall 1006 from 12:30 to 1:30, but sign up on Tartan Connect so you can get that in your email. Our next Smart Safety Connection seminar will be on Tuesday, February 13th, featuring Professor Sean Kian. So watch your email for that invitation as well. Thank you for attending.